through some slides and talk about NRCS Rainfall-Runoff model. That homework 6 is due a week from today, and that's on Blackboard now. NRCS Rainfall-Runoff model was first introduced in the lecture video from Friday's class, and so if you haven't watched that yet, then I think it's important that you do. We'll do some kind of supplementary stuff related to that today, but like the foundation of what we're trying to accomplish by using the NRCS method is described in that video from Friday. So if you haven't already, please catch up and watch that. Any questions before we start? WMS is a software package that we're going to start using next week. We're either going to begin on Monday or Wednesday. I'm not exactly sure yet which day. And so if you'll please install it and have it ready to go by Monday, then that'll make your time in class the most meaningful. It's not an especially resource demanding software package. And for that matter, neither is the Bentley software that we use. So I've posted the installation details I previously emailed to you. I also put that on Blackboard. So if you need the license code or the download link, you can find that on Blackboard. And so please install WMS before next week. It's a great software package and it's going to be really fun to use it. So just that announcement is the last thing I wanted to mention before we revisited the NRCS Rainfall-Runoff model. And so remember that what's above the line, this curved line represents the declining potential infiltration rate. And it's dashed in cases where the precipitation rate is less than the infiltration rate. So we don't have as much infiltration as we would if there was more precipitation. We only have as much infiltration as there is precipitation. So the NRCS method is a way of using land use and soil characteristics to determine something that's known as a curve number. And later on in the class, we're going to use a method called the rational method, where there's a C, a coefficient that you can kind of think of as a percentage. But these curve numbers aren't a percentage. And I mean, you could be forgiven for maybe thinking that they are, since curve numbers have a maximum value of 100. But they're not percentages, and the way that they impact runoff is not linear either. So a small change in curve number can have a dramatic increase in the runoff. There would be some situations where, just as an example, a curve number of 65 in a typical storm would have almost an unmeasurable, because it's so small, runoff. And then a curve number of 70 could be a little bit of runoff, and a curve number of 75 could be really a lot. So you always have to run it through the model to know what the effect is going to be on the precipitation excess. But I just wanted to clarify, because it is a common misperception that curve numbers are a percentage, and they're not. So if we have a rainfall hyetograph on top of the declining rate of potential infiltration, then what's above that, you can see P sub E is the precipitation excess. And so this is a volume balance model, where it's saying that the precipitation, the total quantity of rainfall that's coming from the sky, is the excess plus the initial abstraction plus the amounts that are infiltrated. So there's this reminder about the homework assignment that you're working on right now. On the third problem, what you're supposed to do, in fact, let me just go ahead and bring it up so that we can look at the rainfall data that I provide. All right, homework 6, problem 3. So here's problem 3, and what it's doing is it's saying in the first hour you have 1.5 inches of rainfall, in the second hour 2.5, and in the third hour 1.0. And so these same hints are offered here underneath the table, but what it's saying is that you need to know the cumulative rainfall up to a certain time to find out how much infiltration there's been at a certain time. So for example, at the end of the second hour, the cumulative rainfall is 4 inches because you're going to add together the first pulse of rainfall, which is an inch and a half, and the second pulse of rainfall, which is 2.5 inches. And so think in cumulative terms, although I've just given you the rainfall depth that occurs during each increment. To apply this method, we want to know cumulative quantities. All right, so our book has tables of data that describe different types of land use and different hydrologic soil groups. And we'll browse through a USDA resource. It's a mapping tool in a couple of class periods where anywhere in the United States they've estimated what the soil type is by one of these categories. And it's basically they've gone into the field and done some direct measurements, and then they extrapolate those direct measurements over lots of other areas that have similar topography and similar geological characteristics. And then the hydrologic soil group A is associated with soils that are very sandy and have a high infiltration rate. At the other end of the spectrum, hydrologic soil group D is plastic soils that are almost impervious to infiltration. Very, very poor water passage through Class D soils. Class C would be clay soils and silt soils that aren't quite plastic in nature but still have relatively low hydraulic conductivity, low infiltration performance, and then B is in between. So you can see that this table of curve numbers takes into account the soil type in a given area as well as the types of materials that are on top of that soil. And so I wanted to point out that lawns is kind of a subjective thing that depends not only on what percentage of the area is covered by the vegetation, but then it can also be impactful if it's on a slope versus if it's a horizontal lawn. And so grass that's on a horizontal surface is going to infiltrate more than grass that is inclined. And so some of the tables that you'll see will not only characterize the condition of the vegetation and the hydrologic soil group, but then also the slope of the land as well. And so it's interesting to look at comparisons of different paving materials. So if you think about streets and roads, what we normally have around here is asphalt and concrete. And when you have directly connected storm sewers and gutters that are really efficient at moving water towards inlets and then pipes towards streams, then the curve number doesn't depend on the soil type at all. It doesn't matter if you've got clay soils or sandy soils. If there's an impervious surface on top of it all, then the curve number is fixed. But one of the things that we can do to reduce the amount of stormwater that concentrates is we can have gravel roads, because that infiltrates more. Now that's not appropriate for high traffic areas or in places where people are reluctant to have damage to their vehicles, but there are some places where they'll use like pavers that are similar to cinder blocks and grow grass on top of that in parking areas where it's a low speed, and so there isn't the risk of as much wear as on a road that has a lot of traffic going through. And so there's also pervious pavement, which they have in some places here in town. Huntington has some stormwater regulations that have been implemented over about the last 10 years, so that new facilities that are built are supposed to have on-site storage and detention of stormwater. So the football practice facility is been built since those new regulations came online, and they have some underground tanks for storing water that falls on the roof of the facility and the parking lots. Another one that comes to mind is, the Cookout restaurant that's on 5th Avenue. It has pervious pavement, and you can kind of tell it's pervious pavement because it's always fallen apart. Unfortunately, pervious pavement doesn't do really well in the freeze-thaw cycle, and so if water gets into it and it's not well drained, then as the ice freezes, it can break apart the permeable pavement. And what permeable pavement is concrete is a mixture of sand, gravel, and cement. Well, if you just have the cement and the gravel without the sand, then you'll end up with a concrete mixture that has a lot of voids, and they're interconnected voids so that the water can pass through it. So it doesn't have as much strength as regular concrete, but it also isn't impervious, and it doesn't generate as much runoff. So if we look at the curve numbers, the increasing residential lot size, look at how that decreases the curve number the larger the lot is. And so even for the same soil type, you'll notice if you have quarter-acre lots, you'd have, for hydrologic soil group A, a curve number of 61. And the higher the curve number, the more runoff you're going to have. And when we're thinking of stormwater runoff as a nuisance or as something that's potentially dangerous, then we'd like to have as little runoff as possible. So why do you suppose a 2-acre lot has a lower curve number than a quarter-acre lot? Why is there a lower curve number for a larger lot? Well, the clue is here with this column, the percent impervious. In a quarter-acre lot, some of the lot is grass, some of the lot is roof area, and some of the lot is pavement where people will park their cars. And the larger the lot, the lower the fraction of impervious area. They're more likely to have a large lawn or a garden or vegetated areas that themselves have a lower curve number, and so it's kind of a composite. It's a weighted average. A residential area is a weighted average of grass and roof and pavement and maybe crops of some sort if someone's got a garden. And so certain of the entries on these types of tables are combinations of other base characteristics. So this, for example, is showing woods, brush, types of grasses, and so these curve numbers are much lower in rural areas than some of the curve numbers we're likely to see in urban areas, industrial districts. So if you see an industrial district, the curve numbers are very high because there's not a lot of attention paid to grassy areas in industrial zones, or even in commercial and business areas. Grass doesn't generate profit. Parking lots and strip mall square footage, that's what generates profit, and so that's what they maximize in those types of areas. Any questions about curve numbers? Now, all of the curve numbers that are shown here are under typical moisture conditions, and we call that category 2. Typical moisture conditions. And we have two other ways of either increasing or decreasing the curve number depending on how wet it has been in the past 5 days. And so these antecedent moisture classes can adjust the curve number up or down depending on whether it's been relatively dry, and that's condition 1, or relatively wet, which is condition 3. And so what we can consider the typical normal moisture conditions would be that in the previous 5 days, we'd have between 0.5 inch to 1.1 inches of rainfall. And so usually we'll be designing for the typical condition, but it's also interesting to run an analysis when you've got a watershed and you're trying to figure out how is it going to behave under relatively dry conditions. Then what you could say is, let's do the curve number calculation in category 1, Or in really wet conditions, if you want to find out how a watershed's going to behave, then you could adjust the curve number that you looked up off of this table. This is the typical type 2 or condition 2, and modify it. So just to give you an idea of how much the curve numbers can change, just to put it into this formula, let's say that we had quarter-acre lot in a residential area on Class B soil. So if we go back to the table, quarter-acre lot, residential area, Class B soil. So here's the table, residential, quarter-acre lot, Class B. So that's a curve number of 75. I think it already said that, but I just wanted to illustrate. That comes from the table. So if we have a curve number of 75 under normal type 2 conditions, then how would the curve number be different if there had been no rain in the past 5 days? And so that is calculate curve number 1, curve number category 1. And then in the second bullet point, we're going to look at what would be the curve number if it had been rainy in July. And so it said in July because what we mean by that is it's during the growing season. So we're over the threshold required to put us into category 3 during the growing season. And in this first bullet point, it didn't specify if it's the growing season or not the growing season, because you'll notice that if you've got 0 rainfall, that puts you into category 1, regardless of whether it's dormant or the growing season. All right, so just to summarize, CN of category 2 in this problem is 75. So find CN of category 1, which is the dry, and then find the curve number in condition 3, which is wet. Okay, I've written the substitutions up on the whiteboard, and what you see is that under normal conditions, this watershed has a curve number of 75, but if it's been really dry in the previous 5 days, then that can be as low as 56. And in a situation like that, 56, if it rains in that dry state, it's going to absorb almost all of the water for a typical storm. I mean, you know, a 50-year, 100-year storm is going to satisfy all of the infiltration, and then we'll see some runoff, but it's going to be relatively minor. Whereas under condition 3, the same watershed, the same land cover and soil type, under normal conditions of 75, which is kind of middle of the road, it takes it up to 87. And if we find what kind of comparable conditions is that similar to, a curve number of 87 is kind of like an industrial district. So instead of being a grassy residential area, which we usually think of as generating some stormwater, if the soil's already saturated and it can't absorb any more, it's just only able to absorb as much as gravity allows, then there's going to be a lot of runoff. And so it's good to kind of stress test whatever system you're designing, both to understand what will be the condition, what will be its performance under normal type 2 curve number and antecedent moisture conditions, but then also how is the system going to behave when it's been dry and how will it behave when it's been wet. So you're going to have a design project this semester, and you should keep this in mind, that when you analyze the watershed and you're designing a culvert, that you want to know what does it look like under really the worst case scenario, which is a lot of rain and category 3 antecedent moisture condition. Any questions? All right, now calculating the average curve number in a watershed sometimes is as easy as just coming up with a weighted average. It's never as easy as a simple average. You know, a simple average is where you add the values together and divide by how many of the values you have. And it's the composite curve number is never that simple, because ordinarily a lot is going to have some, let's say, asphalt, some roof, some grass, and you need to know the relative proportion of each to calculate the composite curve number. So an area average, an area weighted average, takes into account how much of the land use is what curve number. And so in this example, if we had a rainfall of 6 inches and we want to find out what is the depth of precipitation excess, then we need to calculate the storage depth with the composite curve number. And so we don't know the area of the watershed, and we don't need to know the area because we're calculating all of these things in terms of depth, not in terms of volume. And so we have the percent land use for each curve number type, and the weighted average, we could do it on Excel. It's always good to start up Excel. We could also do it by hand, but we'll take the land use percentage that's given and multiply the curve number for that land by the applicable land use percentage. And so let me just illustrate. If I take this data table and paste it into Excel, then to make this a weighted average, then I'll multiply the curve number by the land use percentage and do that for each of the rows, and then add them together and divide by 100. And so then the sum of these, and then the weighted curve number is this divided by the sum of, in our case, it's percentages, but you could do the same thing if you had areas in acres, divided by 100. So the weighted curve number here is 86.95. So that's an area weighted average. So what if we had a rainfall of 6 inches? So how do we put it into the NRCS model? What the NRCS model does is it's a way of saying how much precipitation excess are you going to have when you've got a certain storm. So, and the watershed that we've got, the composite curve number, let's say the CN is 86. We'll round 85.95 up to 86. So calculate the storage depth. So the storage is 1,000 divided by 86 minus 10. So the storage is 1.628. And then we substitute that into the formula for the precipitation excess, which takes into account what was the storm size. So P is given as 6 inches. And so P sub E, the precipitation excess, will be the precipitation depth of 6 inches minus 0.2 times the storage. Now 0.2 times the storage is our initial abstraction. So that's why we have the 0.2. We're just estimating that the initial abstraction is 20% of the storage depth. So 1.628 inches. And then that in the numerator is squared. And then divide it by 6 inches plus 0.8 times 1.628 inches. So if we do the calculations there, it suggests that there's going to be 4.41 inches of precipitation excess. So we've got this watershed that has a composite curve number of 86. If it rains 6 inches on that, now we haven't said anything about timing. It's meant to mean like in the same storm. It doesn't mean 6 inches today. I mean, the 6 inches isn't broken up over multiple days. It means in a single event. So 6 inches of precipitation in a single event where the composite curve number is 86. And this 86 is, we're taking into account the antecedent moisture condition. So this is like category 2 because these would be the typical curve numbers. Then there'd be 4.41 inches of precipitation excess in a scenario like this. So that's the NRCS method. It's a way of translating precipitation depth into runoff depth But then the next step, once we know the runoff depth, is the timing. So what we're going to also want to know is how soon after it starts to rain does the precipitation begin to arrive at the outlet. So we're going to use another model to translate precipitation depth into flow rate. But any questions so far about the area weighted composite curve number? This is the easiest, is when we just take an area weighted average. When things get a little bit more complicated is when we have a large impervious area that's adjacent to an area that is not impervious. So a situation like this. So a pervious area, it's shaded green because it's representing grass. So let's say, if we have a curve number of 60 in the grassy area, and the grassy area flows onto the impervious area. So when you have a pervious area connected to an impervious area, what happens is that there's no further infiltration of the grass the grass-related runoff as it's flowing over the impervious area. So if we say this is pavement, which has a typical curve number of 98, then the way that we could calculate the composite curve number is we could use a nomograph like this. And this is just as simple as another area weighted average, but that area weighted average is, the calculations for it are built into this nomograph, where what we have here is 30% connected impervious. And by connected, what it means is it's connected to the outlet. It's directly connected to the outlet. So if we have 3 acres out of 10, that means it's 30% connected. And then here, the grass, the pervious area, has a curve number of 60. So we start at 30 because it's 30% connected impervious, go up to 60, which is the curve number of the pervious section, and then over to the left, you can see it's 72. And let's see, is that just as easy as the area weighted average? It's 0.3, 30% of the area is 98, plus 0.7 of the area is 60. Anybody have a calculator handy and tell us what is the the area weighted average of the curve number? 0.3 times 98, 0.7 times 60, 71.4. So that's consistent with this nomograph method where we're going up from 30, bouncing it off of 60 to the side. Nothing special when you've got directly connected impervious area. But now, what about the reverse? So look at how this has changed. Same watershed shape, the same quantities. We've just moved the impervious area to the top of the watershed rather than the bottom. So look at, in this first scenario that we've just looked at, the runoff from the pavement goes straight to the outlet, and the grass runoff goes on to the pavement runoff. But now, what about the reverse? How is this different? So this is a special case because the runoff from the concrete is flowing over the grass before it gets to the outlet. So this is what we call unconnected impervious area. It's not directly connected to the outlet, but the water from the impervious area has to flow over the grass, and some of that runoff is going to percolate down into the soil because it's flowing over a pervious surface. And so the calculations are different because this approach that we did before of just being an area weighted average, that doesn't take into account that some of the water is infiltrating. So we're generating a certain amount of runoff on this impervious area, but some of the runoff will be lost as it flows over the grass. So we have a modified nomograph now. It's a little more complicated because we have to consider what is the total impervious area and how much of it is unconnected. Okay, now in this example, the total impervious is 30%. So that takes us here, this part of the graph, 30%, and we go up to the 1.0 curve because 100% of this is unconnected impervious. Now, in the next example after this, I'm going to show you this, where some of the impervious is directly connected, some of it is unconnected. And that would be 50%, but this one is 100% of the impervious area is not connected to the outlet. So we start with 1.0 and go sideways from that, and we are intersecting the 60 curve. So here where it says 60, this 60 is referring to the curve number of the pervious area. So it's the green dashed line intersecting with the 60 curve, and then it goes down from there, and then you find the composite curve number. So the composite curve number of this watershed is 65. So it's interesting because it's the same amounts of impervious area, it's the same amount of grass. It's just where the concrete was reduces the curve number. It takes it from 71, which means there's going to be relatively more runoff, down to 65, which there's going to be less runoff because the runoff from the concrete flows over the grass before it gets to the outlet. Any questions about how to read this nomograph? This would make a good quiz question, I think. And then here's this same watershed and the same quantities of impervious and pervious. So 3 acres of concrete, 7 acres of grass. It's just now some of the concrete's directly connected, some of the concrete is unconnected. So we use 0.5 because that's the ratio of unconnected to total impervious. So 0.5 and 30% impervious total area. Intersect the 60 curve because the grass has a curve number of 60, and then down, that takes it to a composite curve number of 68. So it's kind of in between. This impervious area that is unconnected, some of the water that's generated is going to percolate into the soil. So it kind of has a cushioning effect. So why bring all this up? Well, one of the things that they do as a best management practice in parking lots is they'll put in some grass adjacent to the concrete before the water gets into a drainage grate. And one of the buildings I can think of that has this is the headquarters of the DEP in Charleston. They've got an asphalt parking lot, but then they also have grassy sections in between the parking areas. And so, like, if between every row of cars you had a grassy section for the stormwater to run over, some of it's naturally going to be infiltrated into the soil before it gets down into the collection network. And that's a good thing, to have as much infiltration as possible. Okay, so those are all the things I wanted to tell you, clarifying things about curve numbers. Remember that for Monday of next week, you've got the application of this NRCS method, and then please also make an effort to get WMS installed. Are there any questions before we finish for today? I wish I could bank this time because we're going to use it in spades once we start up the WMS. We'll be pressing to get stuff crammed in to then, but for now I'll let you go 12 minutes early, and I'll see you on Wednesday.